Okay, let's have a look at uniform circular motion. Let's look at an object that we spin horizontally. We can make a few observations about that particular object. First of all, if we connect it to a string, we notice that it rotates in a circular pattern, and that the object, even though we're spinning it, it doesn't go faster or slower, unless obviously we put that force on there. Now what happens if we break that string? Well, the second observation that we can make is as we break the string, the object will fly off tangentially to where that string broke. So we can summarise our observations in the following way. First of all, while it's being held by the string, the ball will turn. Second of all, when the string breaks, the ball will travel tangentially to that break point, or the radius of our circle. Thirdly, because the object is turning, there must be some force on that object, otherwise the object would travel indefinitely in one direction. And then finally, we can also see that the force must be directed toward the centre of the circle, otherwise the object would travel out tangentially once again. So this forms the basis of what we call uniform circular motion. So uniform circular motion is the motion along a circular path in which there's no change in speed, hence our object here and our object here have got the same speed, but there will be a change in direction for that object, therefore there'll be a change in velocity. So let's look a bit more closely at what's happening with this object. And this time we're going to look down on the object as we see it rotating horizontally. So at time 1, we know that our object has a velocity v1. At time 2, it's going to have the same velocity. However, we're going to see that the direction has now changed in our circle. We've got our radius of our circle here, and that doesn't change because the object is travelling in uniform circular motion. The distance between our 2 points we'll denote as s for the moment, and we'll come back to that in a second. Now, if we want to look at our velocity or our change in velocity of our object, obviously the change in velocity is going to be equal to v2 minus v1, and therefore we get a delta v here. Now, if we notice what happens with this direction, if we reduce the time down from a large increment here to a much, much smaller increment, we'll notice that this component delta v will actually point toward the centre of our circle. So we can make another observation which says as t approaches 0, delta v will be perpendicular to the original two vectors v1 and v2. So even though our v1 and v2 have the same magnitude, they have a different direction, our change in velocity delta v will always point toward the centre. And because we've got this component that is a vector, delta v, it means that we must also have an acceleration on that object in the same direction, and therefore toward the centre. We call this acceleration centripetal acceleration, and that comes from the Latin derivation meaning centre seeking. So that's okay, we've got a definition. How do we look at this quantitatively? Well, to do that, we need to set up two similar triangles. The first one that relates to our v's, and the second one that relates to our distances. So delta v over our v is similar to our distance of our object moved here over the radius of the circle. And we get this because we've got similar angles, therefore similar triangles. These two magnitudes are the same, these two magnitudes are the same, therefore we can set up this similar triangle relationship between the two components. If we rearrange this, we can get delta v is equal to our v times our distance moved through over our radius of our circle. We know that acceleration is equal to a change in velocity over time. Therefore, if we now rearrange this, taking into account our delta v, we get v times s over r over our delta t from here. Rearranging everything, we now get vs over r delta t. And if we rearrange everything from there, we know that distance over time will give us our velocity. Therefore, our centripetal acceleration will be equal to v squared over r. And similarly, if we've got acceleration toward the centre of the circle, that must be where our force is moving as well. So our force centripetally will be equal to mv squared over r. and that comes from our force is equal to mass times acceleration. Now that's all well and good, but how do we know what v is? Well, let's come up with a new definition that relates time and distance. So we're going to call capital T the period for one revolution. And we're going to have a look at v equals s over t. We substitute in the value for one revolution in terms of the distance travelled, so 2 pi r, over this value here, which is our capital T. So our velocity for our object is 2 pi r over t. Let's have a look at how we might apply this to a problem-based question. So we have a 150-gram ball that revolves uniformly in a horizontal circle of radius 0.6 metres. We see and observe that the ball takes about half a second to travel around that one revolution. First of all, we want to find the velocity of the object, the ball. We then want to find the centripetal acceleration on the object. And finally, we want to know the centripetal force on the object. So as we do with all of these problems, we draw a diagram first. So our object is travelling around this circle of radius 0.6 metres. We know that the period, or the time that it's going to take for one revolution, is 0.5 seconds. We know that the mass of the ball is 0.15 kilos, 150 grams. So the first thing we're looking for is the velocity of the object. We use our equation v equals 2 pi r over t. 2 times pi times 0.6 over 0.5 gives us 7.5 metres per second. Our second part of the question is asking for the centripetal acceleration. So we substitute our value of 7.5 metres per second into this equation. Our radius of the circle gives us a centripetal acceleration of 94.8 metres per second squared. And just to put that in context, 94.8 over 9.8, which is acceleration due to gravity, tells us this object is moving with an acceleration of approximately 10 g, so a large acceleration. Our third part of the question is asking us for the centripetal force. So we're going to substitute in our F equals ma into our F equals ma equation. So we've got 0.15 kilograms, 150 grams, times our centripetal acceleration, which gives us a final value for our centripetal force of 14.22 newtons. So that's how we use our centripetal acceleration equations to calculate centripetal acceleration or centripetal force.